Hello guys, this is Sumant here. Today we'll be covering this lecture, layout strategies from the 12th edition of Operations Management by Heiser and Munson. And the last chapter of location strategy, once we've decided where we want to open up the business, then within that business, how do we want to lay out the individual components of the business such that it's the lowest cost. Um, Now, there are a few things that are highlighted in this chapter by the authors. Uh, One of them is, let's say, the relationship charts, which is subjective. And then also, if we want to go for solving the problems wherein we minimize either the distance traveled or the volume traveling between the different stations, workstations, or both. So if we were to combine them, this is the same uh, process that we've come across many times, including linear programming, project management, and the places where if X is the volume and C is the cost for transporting that X between the pair of I being the origin, J being the destination. So in a small layout process, if you're going from, let's say, reception to the storeroom, then the number of parts going from reception to storeroom times the cost of all of those units. That is how we keep calculating or summing up the cost for all the movement across all the workstation to come up with the total cost, and that is what we try to minimize. To give you another idea, if the textbook does talk about the example of somebody going to the hospital, so a process-oriented layout. So how if a patient comes in, what all work cells do they have to go to? Radiology, ER, or X-ray, and so on. Now, using the same Xij times Cij, where X is the number of units going from I to J, and C is the cost of taking the unit from I to J, then the total cost we come up has to be minimized until and unless there is some precondition wherein certain movement is not allowed or a certain process has to happen before the next process has to begin. Now, we have also come across those concepts from the chapter of project management. So then we have to take those two things into account together. Next thing that is introduced in this chapter is the takt time. Takt time is also referred to as cycle time, which is the total work time available divided by the units required to satisfy the customer demand. So, for example, if there are 8-hour shift, 60 minutes in 1 hour, 6 8s of 48, so there are 480 minutes available in the day for the working. The number of units required to satisfy customer demand can be taken as, let's say, the total demand expected at a pizza shop is about, let's say, 400. Yeah. Now, if the total time available is 480, then the total daily demand would be 400. So 480 divided by 400. Okay. Now, the workers required is also same as the number of workstation required, which is equals to the total operation time required for one single for making one complete finished unit. So let's say for making the pizza, you need half an hour to knead the dough. Then certain 5 to 10 minutes amount of time for adding all the toppings on the pizza, and then baking for another 20 minutes or so. Let's say the total amount of time to bake a pizza is about 65 minutes. Then the number of workstations or workers required would equals to the total time required with 65 divided by the takt time that we calculated, which would be 480 by 400. Let's say that comes out to be 1.2. Yeah. Now, in this case, it would be 65 divided by 1.2. That means that this is how many workers should be running simultaneously, or this would also be the same as a proxy for number of ovens that should be working simultaneously in order to get to the units required to satisfy the time. Okay. Now, The last thing that is not in the PowerPoints is the efficiency. Okay, the efficiency is given to us in the textbook, which is calculated as sum of all the task time. So the complete time it takes to make one unit divided by the actual number of workstation and largest assigned cycle time. Okay, so let's see how what type of problems we can come up with that we may have to deal with in this chapter, and then accordingly we move forward. So let's say we have a problem wherein there are three departments of milling, drilling, sawing, and we are given the volume of the units that are moved between the different workstations of milling, drilling, and sawing, and we're also given the corresponding distances between them. So if you can see, the distance between drilling, the number of pieces going from milling to drilling is 23, and also the distance between milling and drilling is 20. So going by the convention of summation of x I j c I j, our idea is to minimize this thing. Yeah. Now in this case, x m to d is 23, and x m to d is 10. Yeah, so the product of these need to be summed up. So let's say this would come out to be 23 times 10 plus 32 times 5. Yeah, 32 times 5 plus 20 times 8. Yeah, so plus 20 times 8. Now since we have already used to this concept of summation of the products, so let's go ahead and use that and calculate that in a single cell. It'll be easier. Now let's say sum product of the volumes times the distances. Now it is also told to us that there's a cost associated with moving one unit for one feet. Yeah, oops, this should be black. Now it's been given to us that it costs $2 to move one work piece by 1 feet. Now this is all of these number of pieces moved all of these number of feet. So if the cost given to us is $2 for one, therefore our total cost would be this times this. So under the given information, this is the cost. This is the total cost. Yeah. Now in a similar variation of the pizza example that I was talking about, we have a question wherein Leon, like one of the textbook problem from the back of the chapter, we have an expected number of 250 units. The total time in the work day is given to us as 420 units. So first things first, is how much are we expected to spend the time in making one unit. Yeah. So if we know that cycle time or takt time is given to us as the total number of minutes available in the workday is 420. Let me make this like this, so in case something changes I don't have to redo it. And expected number of units is 250. So this is in minutes per unit. Okay, so this is how many minutes we should be spending in making one unit. If that's the case, then number of employees who should be working simultaneously or workstations, or same as number of people need to be cross-trained, would be the summation of all the tasks, which is summation of all the tasks that it takes to shearing, bending, welding, cleaning, and painting. Okay, divided by 1.68. So this comes out to be 4.76. Therefore, he needs to train at least 5. Let me do that here itself. Round up. Usually we don't do that, but we can justify that in our what do you call explanation. So that's how we should do. Lee cross-train 5 employees. Yeah, because there would be no such thing as 4.76. Now, however, in case you do want to round it up, then this is how you would do it. Okay, so theoretically you should cross-train 5 employees. In addition to calculating cycle times or number of workstation or number of people that need to be cross-trained, we'll have the combined condition of the precedence of the activities, where certain activities have to be completed before some other activities can be started. So in this case, we are given the task and the time it takes. We are also given the immediate predecessors. Yeah, so let's get to our basic. So first we have tasks A, and so okay, let's see what all information are we given. First thing that we are given is we know the rate of the goal to produce 180 PDAs. So the rate of production is given to us as 180 per hour. Now if you notice, the time given to us is in seconds, so I'm going to convert this somehow into the seconds. Yeah, so 180 per 60 minutes, right? Or I can say 60 times 60 seconds. Yeah, so this is still equivalent, which means this is in 3600 seconds. Therefore, now if you were to calculate cycle time, cycle time is what? Time available divided by units required. So the time available given to us 3600 divided by 180 units required in this much time, which comes out to be whatever. I mean, we can calculate here, but we'll do that in the spreadsheet as well. So 18 2s are 36 and 0. Okay, so about 20. So 1 unit should come out finished in every 20 seconds. Yeah. Now let's calculate this in our spreadsheet the way it is given to us. So the units required is 180. Let me bring this here. So units required 180. Oops. And time allotted 1 hour, or equals to 60 times 60 seconds. Therefore cycle time would be 3600 divided by 180. So this is in seconds per unit. Now, why are we doing this in seconds per unit, or why not in hours per unit? Because it was given to us as in hours, right? There's a reason. If you notice, we are given this time in seconds, so it is better we calculate our values in seconds as well, so then we can make sense of this when we have to use the values. Yeah. Now the next thing is, what is the theoretical minimum number of workstations? So since we calculated already our value in seconds per unit, we can use it to say what is the total time that it takes to manufacture any one single unit. Okay, so the total time it takes to complete sum of all the tasks to complete one single unit divided by 20. Now you see, if the all of our, hold on, so when we are dividing the sum of all the activities that it takes to produce one unit is in seconds, we can divide that by this number, which is a cycle time, 20 seconds per unit. Now this is the units for this is in seconds. This is divided by seconds per unit. When you do that, this gets cancelled out, this goes on the top, and that is why this is feasible. Yeah. So now we know that we need at least 3 workstations that should be working simultaneously for us to achieve the production rate of 180 PDS per hour. Now let us see how would that be possible. Now if we were to arrange, we have our little diagram here. So if cycle time has to be 20 seconds per unit, now let's say, if you notice, 12 and 8 gives us 20, 15 and 5 gives us 20, and this alone gives us 20, which means if A and C were to be put together in one single cell, okay, B and D were to be put together in another cell, such that this works in 20 seconds cycle and E would work in 20 second cycle. So at, let's say, every 20 seconds, A would send a product to B, C would send a product to D. Initially on the start of the day, C would start after A has finished the first cycle of 20 seconds. But after that, every 20 seconds, A and C would send the products to B and D. And then every 20 cycle, D would send further finished product to E. So to answer, can the theoretical minimum actually be reached? Yes, it can be reached. So the answer would be yes, and this is how we will explain how. That A and C can be combined together in same work cell, and B and D can be combined in second cell, and E can be the third work cell. So yes, the theoretical minimum of 3 workstations can be achieved by assigning all of these tasks of A, B, C, D, and E, which are multiple tasks. They can be assigned over 3 workstations. And that's about it. And there's one more variation of the problem, which is the calculation of efficiency. It is not covered in the lecture notes, but just to give you, it's a very simple process. Let's say if you were to calculate the efficiencies, yeah. In your textbook in the 12th edition, it's on page number 391, which says that efficiency is summation of task times, yeah, this is summation, divided by the actual number of workstations times largest cycle time. So theoretically, if we were to calculate the efficiency for this one, we have the summation of all the tasks is 60 seconds, yeah? All of the summation of all of these tasks is 60 seconds divided by the actual number of workstations, which we calculated as 3, correct, times the largest cycle time, which is 20, okay? So in this case, if we were to achieve this, then our theoretical efficiency would be 100%. Now, again, remember this is theoretical, okay? Now, if we were to go back to a previous question and then calculate, okay? Let's see what that comes out to be, okay? Just remember the formula here, yeah? Okay. If we were to calculate the efficiency here, now if you were to calculate the efficiency for the last question, it should come out to be something similar, following the same path, okay? Now, I mean, that's all about it from this chapter. I hope you guys enjoyed it. If you have any questions or comments, you can shoot me an email. Thanks. Have a nice day. Bye.